Okay, so the mean value theorem, what it says is that you consider a function over a closed bounded interval, and on that interval that function has an average value, right? And what it says is that the average value is the same as the the average rate of change of that function. And mean value theorem says that the average rate of change of f over an interval is the same as the instantaneous rate of change of f at some point in that interval. Now, instantaneous rate of change is given by what? The derivative, right? The derivative at a point gives you the instantaneous rate of change of f at that point. So again, mean value theorem says the average rate of change of f over an interval, over a closed boundary interval, is the same as the instantaneous rate of change at some point. So how do I write it down? Well, it says the following. So this is the mean value theorem. It says that if f is continuous on the closed bounded interval from a to b, and differentiable on the interval from a to b, then we could say that f prime of c is f of b minus f of a over b minus a, and for some c inside of AB. So if f is a continuous function, differentiable function on the interval from a, differentiable means that the derivative exists at every point between a and b, then the instantaneous rate of change at c is the same as the average. This is the average rate of f, rate of change of f in that interval, right? Because you're evaluating the value of f at b, you're evaluating the value of f at a, you're subtracting and then dividing by the length of the interval. So that's the average rate of change of f in that interval. Now, think of this in the following way. Let's say you're going from here to Columbus, and f of t expresses your distance function, okay, from Ada, let's say. So f of t tells you how much distance you have covered after time t, okay? So let's say f of t is your distance function as you go from Ada to Columbus. And then let's say we look at one interval during your ride, and in that interval AB, if I look at this quantity, what is this quantity then? So this is the distance covered at time B, right? F of B. F of A is the distance covered at time A divided by B minus A, right? So what does this quantity represent? Yeah. So what does it represent then, the ratio? Average speed, right? So let's say at time A you are at Ada, at time B you are at Columbus, right? So this is giving you the distance covered over the time interval from A to B, right? F of B minus F of A will give you the distance you covered over that time interval from A to B, right? So if you look at F of B minus F of A, distance after time B minus distance after time A, you get the distance covered over the time interval. You divide that by the length of the time interval, you get the average speed, right? So what is it? So what is f prime of c on the other hand? What is f prime of c? F prime of c represents the instantaneous speed at some instant c, right? Between a and b. So c is an instant between a and b. So f prime of c will represent your instantaneous speed at some point, right? So what this is saying is that as you go from here to Columbus, f of t is your distance function. Then we are saying that if the average, so if I say that your average speed during this ride was 70 miles per hour, right? Then wouldn't you agree that there is a time when your instantaneous speed must have been 70?
Yes.
If your average speed from here to Columbus was 70, at some point in time your instantaneous speed must have been 70. Okay, that's what this is saying. Am I making sense? So for any function, what this is saying is that the average rate of change of f over an interval is the same as the instantaneous rate of change of f at some instant.
During that whole time interval,
Yeah.
if you pick a point anywhere in that time.
So it may not be for any point. All we know, there is a time or there is a point where the instantaneous rate is the same as the average rate. Okay. Now, graphically, what this is saying, let me make a graph here and explain to you graphically what's going on. Let's say this is the x-axis. Let's say this is the y-axis. And let's say this is the point. This is the point A f of a, A f of a. And so let's say the graph of f looks like the following. Okay, so this is the point B f of b. So this point here is the point B f of b. So what I have here is the graph of some function f of x over the interval from a to b. So here's a and here's b. And so if you look at the graph, that's it's clear that the derivative of f exists everywhere because the tangent line exists at each point. I don't have a corner point here. And so what is the average average rate of change of f? What's the average rate for f? The average rate is basically f of b minus f of a over b minus a. What's another name for that? What would
F of c?
No, I'm just talking about f of b minus f of a over b minus a. What else do we call that? The slope of this tangent, slope of this line, right? What we are saying then, there is an instant in time. There is a point here somewhere where the tangent line, that's a bad graph, but okay. So what we are saying is that there is a point C where the slope of the tangent is the same as the slope of this line, okay? Because the slope at C is f prime of C, right? The slope here, the slope of the tangent at C is f prime of C, right? And the slope of this line, this guy has slope f of b minus f of a over b minus a. Okay? So there is a C where the instantaneous rate is the same as the average amount. Now, there might be more than one point where this happens, okay? Maybe also at this point here, let's call that point C prime. Maybe at C prime as well, the instantaneous rate is the same as the average rate, okay? Again, if you go from here to Columbus, right, if your average rate is 70 miles per hour, your instantaneous rate could have been 17 at 2 different times, okay? So that's what this is telling us, okay? Any questions on what this theorem is telling us? Now, you have to be careful about the conditions. F needs to be continuous over the interval, and the derivative must exist between A and B, right? Okay. Again, the key thing, the way to remember this is average rate of change of F, average rate of change of F is the same as the instantaneous rate of change of F, right? So instantaneous rate is the same as the average rate at some point, okay? All right. Now, there is one special case of this theorem is called the Rolle's theorem, and I'm going to write it as a lemma. This is known as Rolle's theorem. Rolle's theorem says the following. Excuse me. If F is continuous on A to B, differentiable on this interval, and if f of A is the same as f of B, then f prime of C must be 0 for some C in the interval from A to B. Is that making sense? So this is a special case of the mean value theorem. Why? Because remember the mean value theorem, the right hand side was f of B minus f of A over B minus A, but f of A and f of B are the same, so f of B minus f of A is 0. So the right hand side of the mean value theorem becomes 0 because of this extra condition that f of A and f of B are the same, okay? So again, graphically what's going on in this case is that is the following. Let's say what we are saying is the value of f at A and B are the same, right? So maybe the graph looks like this. Okay, so here is let's say here is the point B f of B, and here is the point A f of A, right? Then what is the slope of this horizontal line? Yeah, the slope of that horizontal line 0. What we are saying is that the instantaneous rate at some point C, the instantaneous rate at some point C is 0 as well, right? That's what we are saying, okay? There is a point between A and B where the derivative must be 0. This is a special case of mean value theorem. In the mean value theorem, the right hand side, remember, was f of B minus f of A over B minus A, right? Now we are assuming the f of A and f of B are the same, so it's going to be 0. Now, I mean, Rolle's theorem, so usually when I teach it during the semester, I give a proof of the mean value theorem because that's a very important theorem in calculus. However, during the summer, I just feel pressure to finish the syllabus, so I'm not going to go over the proof. But if you are interested at all, you can come by and we can go over that in my office. So I won't give you a proof of this. Usually the way this proof works is that you prove the special case, Rolle's theorem first, and then use it to prove the mean value theorem, okay? So, I'm not going to give you that proof. So I'm just going to go ahead and show you how to use these facts in solving some problems. So here's my first example. So the question is verify f of x satisfies the hypothesis of MVT for mean value theorem, and then find all numbers C that satisfy the conclusion of MVT. So let's say the function is f of x, which is x cubed minus x, and we are given the interval from 0 to 2. So the first thing that we have to do is verify whether this function satisfies all the hypotheses of mean value theorem over the given interval from 0 to 2. Let's see. Is this function, so what are the conditions? What are the conditions? Number one, is it continuous, right? Is it, you ask yourself, is f of x continuous over this interval from 0 to 2? And the answer is, it's a polynomial function. We know that it's continuous there, right? 2, is f, does f prime of x exist for all x between 0 and 2? Well, the answer is yes again, because we know that a polynomial function is in fact differentiable everywhere, right? Okay. So it does satisfy all the conditions. Now I have to find all the values of C which will satisfy the conclusion of the mean value theorem. What do they mean by that? Well, what they mean is that find all values of x where the instantaneous rate is the same as the average rate of f over this interval. So what's the average rate of f over this interval? The average rate of f over this interval is f of 2 minus f of 0 over 2 minus 0, right? That's the average rate of f. And then I have to find values of C such that the instantaneous rate at C is the same as the average rate, okay? So first of all, what's the average rate? The average rate of F is the average rate of F here. So what is okay? So what is F of 2 minus F of 0 divided by 2 minus 0? Well, what is F of 2? It's 2 cubed minus 2, right? And then what is F of 0? It's 0 cubed minus 0 divided by 2 minus 0. Well, basically I get 6 over 2, right? Which is what? So this is the average rate of F over this interval, right? From 0 to 2. And now I have to find values of C such that the instantaneous rate at C. Instantaneous rate means the derivative at C. So solve for this derivative, solve for values of C such that the instantaneous rate at C is the same as this average rate 3. Right? And you have to find values of C between where? For C between 0. For C between what? 0 to 2, right? So solve for values of C between 0 and 2 where the instantaneous rate is the same as the average rate. Is everybody okay with that? How do I find values of C? Well, can we find what's the derivative at C? Can we find that? What is f of x? F of x is x cubed minus x, right? So what is f prime of x? 3x squared minus 1. So what is f prime of c? 3c squared minus 1, right? You replace x by c, right? Everybody is okay with that? Derivative of x cubed minus x is 3x squared minus 1, and then you replace x by c, okay? So then what I get here is 3c squared minus 1. That's equals to 3. And so now I get 3 well, let me finish it off on the board, okay? So what you have then is 3c squared minus 1 is equal to what? 3. So what is 3c squared? Would be 4. So c squared would be, and then what is c? C would be, you take either plus or minus 2 divided by root of 3, right? Because root of 4 is 2, and then you have root of 3. Yeah, is everybody okay with that? I guess I might have to just kill it.
Nothing we can do about their software. That's Microsoft's problem.
OneNote is not responding, so I'll just restart, right?
No, well, it's just a OneNote, so yeah.
Yeah.
If we
Don't wait for the program to respond, it might take a while.
try to close it. If that doesn't work, then we'll go into, yeah, well, I'm going to go into the task. Well, there's Task Manager, which is, oh wait, we might have something here. Yeah, I know. There it goes. Okay. But if that happens, you go into processes because it gets rid of it. It actually terminates.
Okay.
Okay.
Okay. All right. So again, let me just quickly write this down here. So this would be 3c squared minus 1 equals to 3, and that tells me that c is either okay, so I know that C is plus or minus. Yeah.
You might have 20 processes.
Yeah.
You don't want to just start closing processes though. It's just better to restart the computer because the computer.
Well, I guess what I'm going to do is yeah, I can always use the board. Let me just see one more time. Of course. Yeah.
You can see right there on.
Unless it's people.
It is
Do I have to do anything else with process?
No, that should be alright. But if we, your OneNote,
Yeah.
it's a very large file, so.
Oh, it is. If I change the
Yeah, that might help.
yeah, I've been using the same file.
That is in the same file.
Yeah, all my calculus. Yeah, all of them are there. Yeah. So let me make you a new page.
Was that the algebra page that you used?
Say it again. Yeah, it's from the very beginning. Whatever I had, everything is there.
Make sure you close the first one. It's still running.
Which one?
It's not right.
It's not running anymore. No, it's not running anymore. Okay, so everybody is okay with the last example? Okay. Here's another fact. I'm going to write it as a theorem just because it's a fact that you need to remember. If f is continuous on the interval from A to B, and f prime of x is 0 for all x between A and B. Then f is constant on the interval from A to B. I think it is on A to B. Oops. Okay, so what I'm saying here is that if I have a continuous function over an interval, and if the derivative is 0 everywhere inside of that interval, then f must be a constant function there, okay? Why would that be true? Well, it's true because of the mean value theorem, right? Can someone see how the mean value theorem is applied in this case? Well, if I want to justify that this function is a constant function over this interval, what do I have to do? I have to show you that the value of the function at any two given points are the same. At any two given points in the interval, the value of the function are the same. If I show you that, then the function must be constant there, right? So let's take two numbers. Let x1 and x2 be in this interval from A to B, and in this interval, sorry, I want to take this here, sorry, be in this interval, be arbitrary, okay? So these 2 points are arbitrary points in this interval, and assume x1 is less than x2, okay? So what I want to show is that if I pick any two arbitrary points, then the value of the function at the points are the same. So I want to show f of x1 is the same as f of x2. How? Well, let's look at apply the mean value theorem on the interval from x1 to x2. What does the mean value theorem say over this interval? Well, what's the average rate of change over this interval? It is f of x1 minus f of x2 over x2 minus x1. That's the average rate, and that average rate is equal to what? Must be equal to the derivative of f at some instant c, right? For some c between x1 and x2, right?
Yeah, that's what I...
Oh yeah, it should be f of x2 minus f of x1. I just have a mistake there. Yes. Okay, so, but what do we know? What's the assumption on the derivative? No, the assumption here is that if the derivative is 0 everywhere, right? If the derivative is 0 everywhere, so that means f prime of c is 0, which means this is 0. Well, wouldn't that mean that the numerator of the far right side is 0? So what does it tell you? Is it clear then? Is it clear then f of x2 must be the same as f of x1. Okay, so what we have shown by using the mean value theorem is that if I have an interval from a to b, if the derivative is 0 for at each point there, then the function f must be constant there. So it's a constant function by knowing that. Is everybody okay with that? Everybody's okay with that? Okay. So you have to remember that as a fact, which is should not be surprising to you, right? Because if you have the derivative is 0 everywhere, right? That means that the slope of the tangent at every point is what? 0, which means the slope at each point is what? The slope at each point is horizontal, right? If the derivative is 0 at each point, then the slope, the tangent line at each point is horizontal, so it has to be the graph of f must be a horizontal line, right? Well, then it's constant, right? So it should not be a surprising fact. Okay. Another exercise, I'm going to call it a corollary because we're going to use these two facts later. Corollary means that it's a consequence of the previous theorem. Okay, so if f prime of x is equal to g prime of x for all x between a and b, then the function f of x and the function g of x, they only differ by a constant. Okay, for some constant c. So what this is saying is that if you have two functions f and g, and if they have the same derivative over the interval from a to b, then the two functions they differ only by a constant. And this I should say for all x in AB, okay? So if two functions they have the same derivatives then over an interval from a to b, then they only differ by a constant. They only differ by a constant, okay? So how do we see this? Well, the way we justify this is that look at the function h of x, which is given by the function f of x minus g of x. If I look at this difference function, then if I look at h prime of x, that would be the same as f prime of x minus g prime of x, which by assumption is what? Our assumption here is that the derivatives are the same, right? So by assumption, the derivative, this difference should be 0. And this is for all x between a and b. Okay? So then, h prime, what do we have? The derivative of h is 0 for every x between a and b, right? And what do we know about that? We know that h of x then should be a constant function, right? If the derivative of h is 0 everywhere between a and b, then the function must be 0. Sorry, function must be constant. So h of x is c for some constant c. But then it means that h is the same as f of x minus g of x. And then finally I get f of x is g of x plus c. Is everybody okay with that? Everybody is doing okay? So again, these are two facts that we are going to use later. If the derivative is 0 over an interval, then the function must be constant there. And if two functions have the same derivative over an interval, then they only differ by a constant. Okay, they are the same except up to a constant. Okay. Here is an example of that. If you look at the function f of x equals to x to the 4, and if you look at the function g of x equals to x to the 4 plus 10, notice that they have the same derivative, right? They have the same derivative. And notice that they only differ by a constant 10, right? So that's what we are saying. If two functions have the same derivative, they only differ by a constant. Okay. Is this making sense? Okay. All right. Now let's do some real exercises. Yeah, sure. So next question is show that the equation x cubed minus 15x plus 8 equals to 0 has at most one root in the interval between -2 and 2. So what we need to show is that this equation has at most one root between -2 and 2. In other words, if you look at the graph of this polynomial on the left, right, we are saying that show that the graph of the polynomial goes through the x-axis between -2 and 2 no more than once. Okay, it goes through at most at one point only. Okay, so how do I show that? How would I show that? Well, we are going to show this by using proof by contradiction. That is, we are going to assume on the contrary, on the contrary that there are two roots, alpha, beta, between -2 and 2. Okay. So then by MVT, so apply if you don't mind, let me write something here. Let's let f of x be the left-hand side of the equation, and the left-hand side was x cubed minus 15x plus 8. So when we are assuming that the equation has two roots, right, alpha and beta, so it means that f of alpha is what? 0, right? And f of beta is 0. Is that right? Because in the equation, the right-hand side is 0, the left-hand side is my function. So if alpha is the root of the equation, it means f of alpha is 0. If beta is the root of the equation, then that means that f of beta is 0. Okay, so if f of x, so let's let f of x be this, and apply now the mean value theorem on the interval between alpha and beta. In fact, not the mean value, it's the Rolle's theorem, right? I should say Rolle's. It doesn't matter which one you say. Rolle's theorem is Rolle's theorem is a special case of MVT. Okay. So what does it say? It says that if I look at the average rate f of alpha minus f of beta divided by alpha minus beta, the average rate is the same as the instantaneous rate, right? At some number c, so f prime of c, and this is true for some c between what? For some c between alpha and beta, right? You guys agree with that? So if I apply the mean value theorem on alpha to beta, it says that the derivative at some c should be should be equal to the average rate. But however, the average rate here is what? Because f of alpha and f of beta are both 0, right? F of alpha, f of beta are both 0. So then what we have is that, let's go through this one more time. Remember, what I have to show is that this equation has at most one root between -2 and 2. We are assuming, on the contrary, that it has more than one root. That is, it has two roots between -2 and 2. Okay?
What do you mean by root?
Root means this equation has a root alpha. It means that if I replace x by alpha, I can achieve both sides are equal.
Oh,
So it's a solution of this equation.
okay.
So when I say root, it means solutions of the equation.
Okay.
Okay, so we are assuming, on the contrary, that there are two roots in this interval, or solutions. And I'm calling the left-hand side of the equation f of x. So if I say that alpha beta are roots of the equation, it means that f of alpha and f of beta are both equal to 0. Okay? Now I'm applying the Rolle's theorem and saying that by Rolle's theorem, then the derivative of f at some c between alpha and beta must be 0. Okay? Is everybody okay? So if I assume, I made an assumption right at the beginning. I said we are assuming that the derivative, that there are two roots of the equation, and that assumption led us to the conclusion that the derivative must be 0 between alpha and beta. Now remember, alpha is greater than -2 because we assume that alpha beta are between -2 and 2. Okay? So then our assumption that we have two roots led us to the conclusion that the derivative must vanish between -2 and 2 somewhere. And I'm going to show that that's not possible, because what is f prime of x? F prime of x is 3x squared minus 15, right? And notice that the derivative would be 0 if x squared is what? 5, right? Or x is plus or minus root of 5, right? Is everybody okay? Is everybody doing okay? Well, what's wrong here? Well, the derivative vanishes at plus or minus root 5, which root 5 is bigger than 2, okay? So we see that the derivative cannot vanish between -2 and 2, right? So my assumption that I have two roots, that assumption led me to the conclusion that the derivative must be 0 between -2 and 2, but I see that that cannot happen because the derivative is 0 only at the root 5 and -root 5. And that's a contradiction. to my assumption that there are two roots. Okay, so so our assumption of having two roots led us to a contradiction. So that means our assumption was wrong. So so the equation has at most one root in -2 to 2. Is everybody doing okay with what I said so far? Any questions at all? Yeah, go ahead.
I don't get
Mhm.
why we're
Okay, so let's look at the question again. Okay, this is the question. I have an equation x cubed minus 15x plus 8 equals to 0, and the question says prove that the equation has at most one root. Again, root means solution.
So we're just trying to see if the solution is in between those two numbers?
No, we are trying to show that there is at most one root. There is not more than one root in that interval.
Okay.
We are not even trying to find the root. Okay, we are trying to show that there isn't more than one root in that interval.
Okay.
If there is only one. There isn't more than one. Okay, our goal is to show that this equation has no more than one root in this interval. Am I making sense?
Yeah.
So our strategy is that we want to show this guy has at most one root here. Let's assume that it has two roots and see if that assumption leads us to a contradiction. If it leads us to a contradiction, that means the assumption that it has two roots in here is wrong.
Okay.
That's how the proof by contradiction works. Whatever you're trying to prove, you assume the opposite of that and see if you're led to a contradiction. So we have to show that this equation has at most one root, and I'm going to assume that it has two roots. See where it leads us. So if I assume that there are two roots, alpha, beta. So there are two roots, alpha. I'm assuming that there are two roots, alpha, beta in here. Okay, and I am letting f of x. I am letting f of x to denote the left-hand side of the equation. So what is f of x? That's the left-hand side of this equation. The right-hand side is 0. So if I say alpha, beta are roots of this equation, wouldn't that mean that f of alpha is 0 and f of beta is 0? Because alpha is the root of this equation means that when I replace x by alpha, I get that the left-hand side is equal to 0, right? So because I'm calling this f of x, so then alpha is the root means f of alpha is 0. Same way f of beta is 0. Okay? So if I have two roots, then I see that the function f of x has two roots at alpha and beta, right? The equation has two roots at alpha and beta is the same as saying that the function f of x has two roots at alpha and beta, okay? So then I'm applying the Rolle's theorem. Rolle's theorem says that if f of alpha and f of beta are the same, then the average rate is 0, right? So the derivative at some number c would be the same as f of alpha minus f of beta over alpha minus beta. which would be equal to 0 because these two are the same. And this is for some c between alpha and beta. What does it mean? It means that if I assume there are two roots, then I see that the function f has a, the derivative of the function f vanishes at some number c between -2 and 2. So my assumption that there are two roots leads me to the conclusion that the derivative of f vanishes at some number c between -2 and 2. However, we know exactly what the derivative of the function f is, and we know exactly where the derivative vanishes, which is at root 5 and -5. So that's the contradiction. My assumption leads me to the conclusion that the derivative must vanish at some number between -2 and 2, but I know exactly where the derivative vanishes, which is, these are not points inside -2 and 2. So that's the contradiction. Okay? Any other questions?
So
Yeah.
does the equation have a root? So are we not finding the answer, or?
No. You have to understand that we are not trying, the goal is not to find the root of the equation. The goal is to show that it has at most one root. If I have to find the solution, then I would say find the solution of the equation, right?
Okay, so
I would be saying find the solution. So again, we are not even showing that we don't even know that there is one.
what we're trying to prove is.
We are saying that there is no more than one. We are proving there is no more than one. We are not even trying to show that there is one.
Okay.
We are not even trying to find what the solution is. Okay?
Okay.
All we are saying that there is no more than one. But if there is one, there is no more than one. Okay, that's all we are trying to show. Okay? All right. This is the end of this section 3.2. Okay, so let me write down the homework for this section before I move on. So this is section 3.2, and okay, problem 3. Okay, and problem 9. Problem 13. And problem 17. Also problem 5 and 7. Okay, those are very quick answers, 5 and 7. So let me say that again. 3, 5, 7, 9, 13, and 17. Everybody got that? Okay. All right, so the next section that we're going to move on to is the section that we're going to start next. I'm going to take a break for 5 minutes right now. The reason is the next section is a longer one, so I'll be spending 1 hour and 20 minutes on that, okay? The derivative, so we want to know what the derivative and the second derivative tells us about the graph of the function. Okay, that's what we want to determine. What the derivative and the second derivative tells us about the graph of a function. And so we're going to start out with the definition. We are going to say that the function f is increasing on an interval I if for any x1 comma x2 inside of I, we have f of x1 less than f of x2 whenever x1 is less than x2. Similarly, we define f is decreasing, and I'm just going to say dot dot dot, okay? So f is decreasing would mean that f of x1 is bigger than f of x2 whenever x1 is less than x2, okay? So let me show you graphically what it means to say that f is increasing over an interval and decreasing over an interval. So here's an example. So let's say this is my x-axis here, y-axis here, my x-axis here, my y-axis here. Okay, so if I have a function which is increasing, it means that the graph is rising up from left to right, okay? Whoops. The graph is rising up from left to right. So here's the interval, and the function is increasing here. So notice that what it means is that if I pick any x1 less than x2, right? x1 would be less than x2, and x2 is right here. And the way we define it, we said that the function is increasing if f of x1 is less than f of x2 whenever x1 is less than x2, right? So as you go from left to right, the graph is rising. That's what it means, right? The height of the graph at x2 is bigger than the height of the graph at x1. So that's what happens when the function is increasing. And decreasing would mean that the graph looks like this. I mean, there are other possibilities, right? I mean, the graph might be decreasing in some other way, but what we are saying basically is that here is x1 now, and here is x2 now, and now the height at x2 is smaller than the height at x1. Okay, so if the graph is decreasing, it means that whenever x1 is less than x2, f of x1 is bigger than f of x2. Yeah. Yeah, for both of them, that's the case. x1 is less than x2 in both cases. I'm saying whenever x1 is less than x2, the value at x1 is bigger than the value at x2. That's why it's decreasing. Here, whenever x1 is less than x2, f of x1 is smaller than f of x2, so it's increasing. It's rising here, it's decreasing here. Okay? So that's what we mean when we say that f is increasing on an interval or decreasing on an interval. Is everybody okay with that? Everybody understands the definition, okay? Here is an example. If I have the function f of x, which is x squared, if I ask you determine where this function is rising or where this function is increasing and decreasing, what would you say? Everybody knows here the graph of the function x squared, right? So f of x is increasing where? Increasing on what interval, and f of x is decreasing on what interval? Anybody? Yeah, it is increasing from 0 to infinity. It is decreasing from negative infinity to 0. Is everybody okay?
It doesn't include zero, does it?
It does. Let me give you the graph. The graph of the parabola, remember, is
Slope zero.
yeah, but let me explain to you why I'm including 0, okay? So here's the graph of the parabola, and if you look at the interval from negative infinity up to 0, including 0, wouldn't you say that whenever I pick x1, x2 in that interval, f of x1 is bigger than f of x2, right? Whenever I pick x1 less than x2 here, f of x1 is bigger than f of x2. Even if you pick x2 to be 0, that's true, right? So f of x1 is bigger than f of x2 whenever x1 is less than x2 here, including 0. So x2 could be 0. Still, it is true. Same thing happens here. If I pick x1 less than x2 here, notice that whenever x1 is less than x2, f of x1 is less than f of x2. So that means the graph is rising up. x1 could be 0 and still is true, what I said. So that's why I'm including 0 in this answer. Okay, so that's one example. But now, what we are going to, the next theorem will tell us what the derivative tells us about where a function increases and decreases. Okay, so here's the theorem, and this is what it says. Suppose f is continuous and differentiable on an interval I, then number one, if f prime of x is strictly positive for all x in I, then f is increasing on I, and 2, if f prime of x is negative for all x in I, then f is decreasing on I. Okay, so basically this is saying if the derivative is positive on an interval, then the function is increasing on that interval. If the derivative is negative on an interval, then the function is decreasing on that interval. Okay, is everybody clear on the statement? You guys are clear on the statement? So notice that, let me show you graph. See, derivative is positive and negative means the slope is positive and negative, right? So notice that if the graph looks like, if the graph of the function looks like this, and if you look at the slope at any given point here, Wouldn't you say that the slope is positive? Okay, and even if the function rises up like this, let's say, so it might increase in this way, then what's the slope at any given point? Well, the slope is positive again, right? Everybody sees that? So when the derivative is positive, then the function is increasing on that interval, okay? The same way, if you have a decreasing curve, you'll see that the slope would be negative, right? Because if you have a decreasing curve, then the slope at a point will look like this, and that has a negative slope. Okay. Now I want to go over a couple of examples of using this. First example, suppose that I have the function f of x is equal to x to the 1/3, and I want to know where the function is. So the question would be phrased in the following way: determine where this function is increasing and decreasing, okay? Where this function, so on what intervals is this function increasing, and on what intervals is this function decreasing? So again, we know that we can determine that by looking at the derivative. If the derivative is positive on an interval, we know that it's increasing, and if negative, it's otherwise, right? So if I look at the derivative in this case, what's the derivative? We know that by power rule, it is what? It is this, right? So this would be 1/3 x to the what? Negative 2/3, which is what? I'm going to write it as x to the 2/3 in this way. Everybody agrees with that? You guys are okay with that? 1/3x to the 2/3. So if that's the derivative, right? So notice that the derivative. So I want you to answer the following. Can you determine, if you look at the real number line, right? So let me make a real number line. If I look at a real number line, notice that the function is defined everywhere, right? The domain is everything, and here is the number 0. Okay. Can you tell me on what intervals is this derivative positive, and what intervals is this? That is, for what values of x is this derivative positive? For what values of x is this derivative negative? Can you say that? The derivative doesn't exist at 0, right? So that's why I wrote that. I plotted the point 0 on the real number line. Now you tell me whether this for what values of x is this derivative positive, and for what values it's negative.
Well, since 3x to the 2/3 is equal to the cube root of x squared,
Yeah?
that means there are no negative x.
Yeah, I have a square. Very good. So I have actually 1/3 squared there, right? This thing here, what he's saying is this is 3x to the 1/3 whole squared. So this derivative is always positive no matter what x is. It doesn't exist at 0, but otherwise...
Isn't it x squared times to the 1/3 power?
Oh, it's the same thing as saying that actually 1/3 to the 2.
Oh, you're right.
Right? So what's the difference between writing actually 1/3 to the 2 and x to the 2 to the 1/3? Either case, you multiply the exponents, right? Okay, so what we see is that the derivative of the function is positive everywhere, right? So what does it tell me? It tells me that the function f, we know that is increasing everywhere, right? So I know that my function f is the function f. My conclusion is f is increasing where? The function, you see, the derivative doesn't exist at 0, but the function is defined at 0. Right? It's actually 1/3. So the function is in fact increasing everywhere from negative infinity to positive infinity. Okay. So because I know that it increases up to 0, right? And then it is going to increase after 0 as well, right? And I know that the function is continuous at 0, right? So if you have a continuous function which increases up to 0, right? And it is increasing after 0 as well, because it's a continuous function, then I know that it's increasing everywhere, right? Altogether. Am I making sense? Is everybody okay with that? So, and remember the graph of the, I think I gave you the graph of actually 1/3 before, right? And I think what I gave is the following. Anyone remembers the graph? In this case, it looks like this, right? Okay. What's that? This is the graph because it's increasing everywhere. Actually, 1/3. The function was actually 1/3, okay? And the graph of that function is given by this, okay? All right, so the function is increasing everywhere. Now let's look at the a second example. You can compare that with the example when we have actually 2/3 instead. So if I have the function f of x is actually 2/3, let's see what happens then. In this case, what's the derivative? Again, this function is continuous everywhere, right? Because it's not even root, it's an odd root, right? 1/3. So it's continuous everywhere. What's the derivative here? It's going to be 2/3. Actually what? 2/3 negative 1/3. Very good. So then I get what? 2 divided by 3 times actually 1/3. So now what? Again, the derivative does not exist at 0, right? So notice that if I make the real number line, I know that the derivative doesn't exist at 0. What's the sign of the derivative on the left of 0? When x is less than 0, what's the sign of the derivative? Negative, right? Because if x is negative, actually 1/3 is negative. So I know that my derivative f prime is negative everywhere here. So whenever x is on the left side of 0, the derivative is negative. And whenever x is greater than 0, actually 1/3 is positive. So I know that the derivative is positive here. Is everybody okay with that? So then I could say that the function f is doing what? The function f is decreasing from negative infinity to 0 and increasing from 0 to infinity, right? Is everybody okay with that? All right, and I think I gave you the graph of this guy before as well. Let's recall what the graph was. My x-axis, my y-axis, and the graph looks like the following. So up to 0 the function is decreasing, and after 0 the function is rising, right? It's increasing. Is everybody okay? It is defined and continuous at 0. Okay. Any questions on what we did there? Okay. Example. Suppose I have the function g of x is equal to x to the 5. Anyone can tell me where this function is increasing and where this function is decreasing? Where? Without any work, you should know. Yeah, because remember when I reviewed the algebra, I said the graph of powers of x, right? If it's an even power of x, then the graph looks like a parabola. If it's an odd power of x, then it looks like the graph of x cubed, right? And the graph of x cubed is rising everywhere, right? So it's increasing. So I know that g is increasing. This is increasing on negative infinity to positive infinity. Which is not, so we can also check how the derivative look like here for this function. If I look at the derivative, right, notice that the derivative is 5x to the 4, right? And notice that the derivative is 0 at what point? The derivative is 0 where? In order to determine where the derivative is positive and negative, you have to first figure out where the derivative is 0 or does not exist. The derivative is 0 in this case at 0, right? So it cannot be positive or negative, it's just 0 at this point. And now look, when x is negative, note that x to the 4 is what? So the derivative is positive, right, when x is negative? And it is positive when x is positive, right? So that's why we have that the function g is, I know that the function g is increasing up to 0, and it also increases from 0 to infinity, but because the function is continuous at 0, I could say that it's increasing all the way like this, right? Okay? Alright, so I'm not going to even try to draw the curve here because we know that the graph looks like the graph of x cubed. Okay, now these are the easier examples of determining where a function is increasing and decreasing. So now problems more like what you might see in exams. So let's say I have the function f of x, which is given by 3x to the 4 minus 4x cubed minus 12x squared plus 5. Suppose that I have this function. Again, the question is, where is this function increasing and decreasing? And let's look at the derivative, okay? So because we're going to use the derivative to determine where the function increases and decreases. What's the derivative in this case? 12x. Very good. 12x squared minus 24x. Okay, now before you determine where the derivative is positive and negative, you have to find where the derivative is 0 or does not exist, right? So that is, you have to find the critical point. So if I ask you where a function increases or decreases, the first step is you find the derivative, okay? The second step, you find the critical points. Find the critical points. So how do I find the critical points? Well, I solve the equation f prime of x 0, right? Which would mean that 12x cubed minus 12x squared minus 24x is 0. What can I factor out first? 12x, very good. So I get x squared minus x minus 2, right? And can I factor out the quadratic here? What is that? X minus 2, x plus 1. And so finally, what are the solutions? X could be 0, x could be negative, x could be 2, or x could be negative 1, right? So these are the critical points that I get. Now, I also have to solve where the derivative doesn't exist, right? Solve solve f prime of x does not exist, but in this case no solution, right? Because we see that the derivative is what? The derivative is it's a polynomial function. The derivative is given by this guy, and it exists for any x, right? So the derivative exists everywhere. So now what I'm going to do is make a real number line.
Is that the third step?
This is the solve for the critical points, and the third step is what I'm going to do now. The third step is what I'm going to do now, which is make a real number line. And on the real number line, what you need to do is plot the critical points. So I have the critical point at -1, the critical point at 0, and the critical point at 2. Okay. Once you plot the critical point, this is what you have to do. You have to figure out the sign of the derivative at each subinterval. So you get a subinterval up to -1, and then you have between -1 and 0, between 0 and 2, and then up after 2. So we got 3 critical points. These 3 critical points will divide the real number line into 4 subintervals. And you have to determine what's the sign of the derivative on each subinterval. Am I clear? So what's the derivative? Let's go back to the derivative. Now remember, the derivative is basically the left-hand side of this equation, right? So I'm going to go ahead and write down the fact that this derivative is 12x times x minus 2 times x plus 1, right? We factored out the derivative this way. Is everybody okay with that? Now you tell me, look at this derivative. Can you tell me what's the sign of this derivative when x is to the left of -1? When x is less than -1, is this derivative positive or negative? Okay, let's decide. When x is less than -1, this factor is negative. When x is less than -1, this factor is negative. When x is less than -1, this factor is 3 negative makes it negative. So I know that the derivative is negative here, negative. So this is where I'm looking at the derivative. Okay, between -1 and 0, is this derivative positive or negative? Well, you're just making a good guess, right? Or did you actually plug in? Between 0 and 1, right? When x is between between -1 and 0. When x is between -1 and 0, this guy is negative, right? This guy? Negative, so positive. But this guy now is positive, right? So I know I have a positive here. Don't assume that these signs alternate for any given function, okay? Because there are functions for which it's not going to alternate. Am I making sense? For example, we looked at x to the 5, right? For x to the 5 at 0, right? It was positive and positive on both sides of 0. So yeah, you really have to check it. Between 0 and 2. Between 0 and 2, yeah, it's going to be negative, but let's just go through the checking. Between 0 and 2, this guy is positive. This guy is negative. Between 0 and 2. And this guy is positive. So positive, negative, and positive, right? So that's negative. And after 2, I'm going to be bold, and without checking, I'll just say plus, okay? So what do we have? We have that the function is decreasing up to -1. After -1 up to 0, it's increasing. After from 0 to 2, it's decreasing, and from 2 to infinity, it's increasing, right? Is everybody okay? So I'm going to write, how am I going to write this? I'm going to say f is decreasing on negative infinity to negative 1 and on sorry, I'm going to write this, and on 0 to 2 f is increasing on negative 1 to 0 and on 2 to infinity. Here's remember whenever I have a critical point where the derivative is 0, right? Negative 1, 0, and 2. At these three critical points, the derivative is 0, right? Now, when the derivative vanishes at a point, remember I told you there are three possibilities, right? Maybe the graph looks like a upward parabola at that point, or maybe the graph looks like a downward parabola at that point, or at that point the graph looks like the graph of x cubed. Now, at negative 1, which one is the case? That is what I'm trying to ask. At negative 1, do I have a local max or a local mean? At negative 1, do I have a local max or a local mean? Local mean, right? Because what's happening to the left of negative 1? Decreasing, and then it's increasing, so negative 1, I have a local mean. What's happening at 0? Local max, 2, local mean again, right? So let me label that. So this would be, so I have a local mean at negative 1, I have a local max at 0, and I have a local mean at 2. Determining the local max and local mean in this way is called the first derivative test. So we are determining whether I have a local mean or a local max at a critical point, and determining in this way that is called the first derivative test. Another thing that okay, so let's figure out a couple of things here. I want to sketch the graph of this function for you, okay? And notice how we can graph it now very easily. What's the value of the function at negative 1? What is f of negative 1? What's the function? The function is 3x to the 4 minus 4x cubed, right? So if you plug in negative 1, what do you get? Somebody check. You get 0, right?
Negative 1?
Yeah.
0, yeah.
What is f of 0? That's 5. What is f of 2? Negative 27. That's a big number. Okay, now I want to determine two things. One is, I want to determine the terminal behavior of the function. So what do I mean when I say terminal behavior of the function? Notice that my function is a polynomial function, right? So it's continuous from negative infinity to positive infinity. The domain of the function is from negative infinity to positive infinity. I need to know what is the behavior of the function at infinity and negative infinity. That is, does the graph of the function goes up always at infinity as you go, as x gets bigger and bigger? Is the function getting bigger and bigger? As x gets smaller and smaller in the negative direction, is it getting bigger and bigger or smaller and smaller, right? So that's what I want to determine here. Well, it's pretty easy for us to determine, right? So this is, I am done with answering my question of determining where the function is increasing and decreasing. My answer is there, okay? Now I'm just doing some extra work of trying to come up with the graph, okay? So what's the terminal behavior in this case? Terminal behavior of f. So what I mean by that is, what is happening to the value of f as x goes to infinity? So as x goes to infinity, what can you tell me about f of x? And as x goes to negative infinity, what can you tell me about f of x? Now, you guys, everyone has the function f of x in front of you, right? It's a polynomial function, right? If I have a polynomial function, as x goes to infinity, what's the limit of that function? Oh, this is my answer is done here, okay? We are done with answering our question of determining where the function increases and decreasing. I'm just trying to give you some extra work of finding out the graph, okay? And I'm going to write down the steps for drawing or sketching the graph of a function later, so you don't have to worry about that now. What's the limit of f at infinity? What did you say? Remember what the function is, right? The function is right here. What's the limit of this function at infinity? Infinity, right? Because if you have a polynomial function, remember what I said, the quickest way of determining the limit is that when you have a polynomial function and you want to know the behavior of the polynomial when x is big, the lower order terms wouldn't matter. Only the dominating term x to the 4 will matter, okay? So what's the limit of 3x to the 4? Infinity, right? And what's the limit of 3x to the 4 at negative infinity? Infinity, because it's 4. So then the limit is infinity here, infinity here. So I now know that as x gets bigger and bigger, the value of the function f is also getting bigger and bigger. And as x goes to negative infinity, the value of the function goes to positive infinity, right? So let's see how this information can help me sketch the graph of this function. And let me be a little bit careful. At -1 I have to get 0, and at 2 I have to get -27. Okay. I might not be able to precise with the scaling here. Okay, the first thing you want to do is you want to plot the points at the critical points. So remember, we determined f of -1 is 0, right? And we determined f of 2. So let's say here is -1, and f of -1 is 0, right? And we saw that f of 0 is 5, and f of 27 is what?
What? F of -2.
No, f of 2 was -27, right? So f of -2 would be 1 right here, and 2 right here, let's say. And you know what? I'm not going to be able to be precise with the scaling anyway. So I'm just going to say this is f of -2. This is this is 2, and f of -2. And this was 0, and then at 0 the value of the function is 5. So let's say 5 is right about here, okay? Is everybody okay with that? So the point here is 0, 5, and the point here is -1 and 0, right? So now I'm going to sketch the curve. What is happening up to -1? Up to -1, remember, at negative infinity, the function comes from positive infinity, right? The limit of the function at negative infinity is positive infinity, and the function is decreasing up to -1, right? So I know that the function decreases up to -1, right? Between -1 and 0, what's happening? It's increasing, right? And between 0 and 2, it is decreasing. And after 2, what's happening? It's increasing. Okay. So that's how the graph of this function would look like. Notice one thing though, when I sketch the graph here, I said the graph is decreasing this way, right? Now why not decreasing this way? Why? So you see what I mean is that how the curve is curved, right? That is how it is concave up or down, right? So when I'm sketching the curve here, I sketched the correct graph, but how did I know that is concave up or is it concave down? How do I know that? Well, I don't know that yet. I cannot tell where the function is concave up and down yet. And for that, what I need is the second derivative. So what we have found is that the first derivative tells us where the function is increasing and decreasing. Okay? The second derivative, where the second derivative is positive and negative, it's going to tell us where the function is concave up and down. Okay? So that's what we are going to look next. Now everybody is clear with what we did so far. Okay, so usually the question will be determine where the function is increasing and decreasing. Another question you might be asked is find the critical points and determine whether you have a local max or a local min at each of the critical points. Am I making sense? What did you do? Well, you find the critical points, and as soon as you make this picture, right? Once you find the critical points and you make this picture, then it's pretty clear where you have the local max and where you have the local min. Is everybody clear? There are two questions here. One is where the function is increasing and decreasing, and the other question that I might ask is find the critical points and determine whether you have a local max or a local min at each of these critical points. And that's what we did here, right? -1, 0, and 2. Those are the critical points, and then we found out whether I have a local max or a local min at each of these points. So the question might be phrased in two different ways. All right, so that's that. Covered all this. Okay, now we talk about the second derivative and concavity, okay? So concavity, so let me make some pictures first. So if I have a curve which looks like this, okay? If I have a curve which looks like this, that would mean it's a concave up curve. So this is a concave up curve. So notice what's going on here is that if I look at the tangent line at any given point, the tangent line lies below the graph. Okay, when you have the function being concave up on an interval, it means that at each point the tangent line is below the graph of the function. Okay. And you can compare that with something which is not concave up, which is concave down. So let's say something like this. Then at each point, the tangent line is above the graph of the function. Am I making sense? Okay. And so here, in this case, this function is concave down. And here it is concave up. Okay. So what should be the definition of concave up and down? By the way, if you look at if I give you another point here, okay, and if I look at the tangent line at this point, which tangent line has bigger slope? The green one or the red one? The red one has bigger slope. So when you have a function which is concave up somewhere, then the slopes are increasing there. If you have a concave up graph, the slopes are increasing there. If you have a concave down, notice that if I look at the slope here, which slope is bigger? The green one again, right? So again, no, sorry, in this case, the slope of the red one is bigger again. So in this case, the slopes are decreasing. So when you have a function, if a function is concave down on an interval, then in that interval, the slopes are decreasing. Am I making sense? So basically, wouldn't that mean that if I want to know where the function is concave up, I basically have to know where the slopes are increasing? Well, slope means the first derivative, right? I have to find out where the first derivative is increasing. If I want to know where the function is concave down, I have to know where the slopes are decreasing. It means I have to know where the first derivative is decreasing. So I can view the first derivative as a function, and then I can figure out where the first derivative is increasing and decreasing it, just like we did it before. So let me just formally write down what's the definition of concavity. If the graph of f lies, number one, above all of its tangents on an interval I, then we say f is concave upward on I. And 2, below all of its tangents on I, then f is concave down on I. Okay, so that's what we said. If all the tangents are below the graph, then the function is concave up. If all the tangents are above the graph, then the function is concave down. And we also noted the fact that when the function is concave up on an interval, then the slopes are increasing, meaning that the derivative is increasing. If the function is concave down on an interval, then the derivative is decreasing there. Okay. Now, how would you determine where the first derivative is increasing and decreasing? Well, the first derivative increases where the second derivative is what? Remember, a function is increasing where the first derivative is positive, that's what we said, and the function is decreasing where the first derivative is negative. What did you say if I ask you, how would you say, if I ask you where is the first derivative increasing and decreasing, how would you answer that? Where is the first derivative increasing and decreasing? Well, the first derivative will increase on an interval if the second derivative is positive there, right? Because the second derivative is the first derivative of the derivative function, right? So wherever the second derivative is positive, the first derivative would be increasing, which would mean that the function is concave. Yeah, so if the second derivative is positive somewhere on an interval, then the first derivative would be increasing there. That would mean that the function is concave up. And if I have that the second derivative is negative over an interval, that would mean that the first derivative is decreasing. If the first derivative is decreasing, remember, then we know that the function is concave down. So again, let's go to the picture. When I have concave down curve, then the slopes are decreasing. Concave up means the slopes are increasing. Okay, so here f prime is what? Decreasing. Here f prime is increasing, right? Slopes are increasing. And here slopes are increasing would mean that the first derivative is what? Second derivative is what? Positive. And if the f prime is decreasing, that would mean that the second derivative is negative. So that means if I want to determine where the function is concave up, all I have to know is where the second derivative is positive. If I want to know where the function is concave down, I have to know where the second derivative is negative. Okay. Is everybody clear on that discussion? Okay, at the end of the day, at the end of this discussion, all I have to remember is to determine where the function is concave up or down, I have to know where the second derivative is positive or negative. Okay, so let's do that in the next example. And I am going to use the same example as I was using before. The reason is I know the first derivative already, so I don't have to do too much work. So f of x is the function 3x to the 4 minus 4x cubed minus 12x squared plus 5. And I think I think the first derivative was 12x cubed 12x squared minus 24, right? X. So that's the first derivative. So I want to determine in this example where the function is concave up and down. So I'm going to compute the second derivative as well. So what would be the second derivative? The second derivative would be derivative of the derivative. So what is that? It will be what? 36 x squared minus 24x minus 24. Okay, I have to determine where the second derivative is positive and negative, and remember, in order to determine that, I have to first of all find out where the second derivative is 0 or does not exist.
It's fine, the second derivative before.
Say it again?
It's fine, the second derivative.
Oh, in this case, the question is where the function is concave up and down, okay? So determine where is f concave up and where is f concave down. So if that's the only question, then the first step is what I did. You find the second derivative, and the second step would be you want to know where the second derivative is 0. So solve where the second derivative is 0. And where the second derivative does not exist. Okay, these are the two things you have to solve. Well, we know that the second derivative exists everywhere because the second derivative, this is a polynomial function, so the second derivative exists everywhere. So all I have to do is find out where the second derivative is 0. The second derivative is 0 where 36x squared minus 24x minus 24 is 0. And I think you would agree with me that I can divide everything by 12, right? So I get what? 3x squared minus 2x minus 2 is equal to 0. You know what? Let me just say this is multiplied with 12, right? Then this is equal to 0. Yeah, I don't know why I did that. Just cancel out that 12. How do I solve this now? I cannot factor it out, I think. So you just have to apply the quadratic formula, okay? So if you apply the quadratic formula, what do I get? Negative of negative 2, because that's the coefficient of x, plus or minus the square root of, plus or minus the square root of what? Negative 2 squared minus 4 times 3 times negative 2 divided by 2 times 3, right? Are you guys okay with what I wrote? Okay. We have to simplify this, and what we would get is 2 plus or minus root of 28, right? Is it? 28 divided by 6, and that's the same as 1 plus or minus let me keep that 2, sorry. Plus or minus 28 is the same as 4 times 7, right? So I get 2 times root 7, right? Divided by 6. You guys agree with that? 28 is 4 times 7, and root of 4 is 2. So that's why I have that. And this is the same as 1 plus or minus root 7 divided by 3. Now you realize that 1 plus root 7 would be positive, but 1 minus root 7 would be what? Negative, because root 7 is bigger than 1. Everybody is okay with that? The reason root 7 is bigger than 1, the easiest way to see that, if you have root of 4, that's 2, right? Which is bigger than 1. So I know that 1 minus root 7 would be negative. So now I make my number line. And on the number line, I plot the critical points. I know that one of them is negative, 1 minus root 7 over 3. The other one would be positive, 1 minus root 7 over 3. If you want, plus, you can approximate these two numbers, okay? If you have a calculator, would you tell me approximately what they are? This one would be approximately what?
0.88.
So this one would be negative 0.88?
Oh wait, hold on.
So which one is 0.88?
Negative 0.54.
Negative 0.54. And this one would be positive 0.54 now.
No, that is
What is that?
0.122.
0.122?
Yes.
0.12. So I'm just going to say 0.12, okay?
No, 1.2.
Oh, 1.2, sorry. 1.2. All right. So one of them is 1.2, the other one is negative 0.54. Okay, now we know, so what I have to do is look at the second derivative and determine whether it's positive and where it is negative, okay? So how do I do that? Well, what was the second derivative? The second derivative is this guy here, right? This guy is the second derivative. I have to determine where this second derivative is positive and negative. The bad thing here, I cannot factor out, right? However, I know that it's a polynomial function. It is continuous everywhere. So I can just determine where it's positive and negative in the following way. You just have to pick a point on the left side of negative 0.54. For example, negative 1. Plug in negative 1 inside the second derivative. So if I plug in negative 1 for x, what do I get? Is it positive or negative? It will be 36 negative 1 squared minus 24 negative 1 minus 24, right? So it will be positive clearly, right? Because, yeah, so it's positive. Everybody sees that? So it's going to be positive here. And so I'm talking about the second derivative here. And then between negative 0.54 and positive 1.2, what number can I pick? 0. Easiest number would be 0. And if I plug in 0, is it clear that I get negative 24? It's negative. It's negative. And what should I plug in from the third interval? 2, yeah. So if I plug in 2, is it clear that, yeah, 4 times 36 minus 2, yeah, you get positive, you realize that? You can use your calculator if you want to, but I do get positive here. So, the second derivative is positive here, that means the function is concave up. Here it is concave down, and here it is concave up again. So here's... So the function f is concave up to the point negative 0.54. It is concave down between negative 0.54 and 1.2, and it is concave up after 1.2. Is everybody okay? So here it's concave up, concave down, concave up. Is that okay? Now remember, I gave you the graph of this function before. Let's see. So what we are saying is that the function is concave up to negative, sorry, not negative 1. It's concave up to some negative. This is where negative 1 is, right? So where is negative 0.54? Somewhere here, right? Negative 0.5. So we are saying up to that point. Let me use red. Up to that point, the function is concave up. Okay. The function is concave up to that point. And then where is 1.2? I think this was 2, right? So 1.2 would be somewhere here. So there is some point here, and up to that point the function is concave down. The function is concave down. But after that point the function is concave up again. Okay, so this will be, again, my scale is bad, so I can't do anything about it now. So from this point, it is all the way concave up, okay? Am I making sense? Does everybody sees that? Okay, so up to the point, this is 1.2, and this is negative 0.54. Between those 2 points, it's concave down, and then after that, it's concave up again. Is everybody clear on the graph? All right.
To get those points, do you just plug it into the first derivative?
Which points?
To get the concave up and down, you just get like the y coordinate of it. Do you understand what I'm saying? Like if you plug 1.2 in, where would you plug that in to get the x or the y
coordinate? Or if I ask you to find... Oh, I haven't told you about the inflection points. Yes. So once I look at this, if I look at this picture here, notice that the concavity is changing at negative 0.54, right? The concavity changes from down to up right at this point here. So that's called an inflection point. So this is an inflection point. Inflection point means it's a point where concavity changes. Same thing happens here, right? The concavity changes from down to up. So this is an inflection point as well. Okay? And so if I ask you, find the inflection points, all you have to tell me is that the inflection points are at x equals to negative 0.54 and x equals to 1.2. Okay? That's all you have to tell me. But usually I ask you to draw the graph anyway, so you would have to find the y coordinate anyway. So you'd have to, where is the graph? Yeah, right here. So you'd have to know what's the height of the graph at 1.2 and negative 0.54 anyway, because you're going to plot the graph. Okay. Is that what you asked?
Yeah, that's exactly what I was asking.
Okay. All right, now I'm going to do more examples, and then you'll see what steps I exactly want you to show. So that example is done there. Is everybody clear on what we mean by the inflection points? Everybody is okay with that? All right, I'm going to take a 1 minute break. All right, so the last thing that we need to do is what we call the second derivative test. So this would be the second derivative test. So what is that? Well, if I have a critical point where the derivative vanishes, right? What did we say about that? We know that if I have a point, say this is the point c f of c in the graph of the function f, and if I know that the derivative vanishes at c, I know that the tangent line is what? Horizontal at that point, right? And then I said there are three possibilities. Maybe the function, if I have a local mean at that point, or maybe it's going to look like this, so it has a local max at c f of c. And another possibility is what? It has neither, right? So maybe it's like that, right? So I have the point cf of c, and at cf of c, the derivative is 0. It means that the slope is 0. Then I may have a local mean, local max, or neither. So the second derivative is a way of determining that. If I have a critical point where the derivative vanishes, I want to determine whether I have a local max or a local mean at that point. Am I making sense? And what does the second derivative say? Well, notice that if I have a local mean, then the function is concave up or down. Concave up at that point. If I have a local max, the function is concave down. So if I want to know whether I have a local mean or a local max at a critical point, all I have to do is determine whether the function is concave up or down there, right? Now, how would I check whether the function is concave up or down at c? If the second derivative is, so notice that in this case, so here in each picture, what I have is that to begin with, the derivative at c is 0 in each picture here, okay? The derivative at c is 0. And so c is a critical point. And we want to know whether at c I have a local max or a local mean. And I see that if I have a local mean at c, it means that the function is concave up at c. And the function would be concave up at c if the second derivative is what? Yeah. And in this case, the second derivative is, and in the, oh, sorry, I should say at c. Okay, and in the other case, we don't know. Okay, so if I know that the function is concave up, if I have a critical point at c, if the function is concave up at c, then I know that I have a local mean. If I have a critical point at c And if I know that the function is concave down at C, then I have a local max. So that's all the second derivative. That's all what the second derivative tells us, okay? So in this case, what do I have? I have a local min. Here I have a local max. Okay, in this case I have neither. Is everybody okay with that? Okay. So the second derivative. So do I need to write that down, or you understand what I'm saying? So second derivative test says the following. Suppose I have a point C where I have a critical point where the derivative is 0. C is a point where the derivative is 0. I want to know whether at C I have a local max or a local mean. So what we are saying is that at C I have a local mean if the second derivative is positive, and at C I have a local max if the second derivative is negative there. Is everybody okay? Second derivative at C negative means local max, positive means local mean. So let me just go over an example, explain how to use the second derivative test instead of writing it down in words. So let's say I have the function f of x, which is given by the function x over x squared plus 4. So what's the question? The question is find the critical points and classify them. So when I say classify them, I mean determine whether you have a local max or a local mean at each of these critical points. Am I making sense? Now, do we already know how to do that? Yeah, remember, if I determine where the function is increasing and decreasing, that's going to tell me exactly where I have the local max and local mean, right? So we know one way of doing that. This is the second way. So why am I doing that then? Well, sometimes in some problems it's useful to use the second derivative test than the other one, than the first derivative test. So what's the derivative? The derivative would be, if I apply the quotient rule, it will be x squared plus 4 squared, right? And then you're going to take the denominator. So that's low, d high is 1 minus high, and what's d low? 2x, right? And what is that equal to? X squared minus 2x, so that's negative x squared plus 4 divided by x squared plus 4 squared. Now, I am going to also find out the second derivative now. The second derivative would be derivative of the derivative. So you take the square of the denominator. If I take the square of the denominator, what do I get? 4 now, right? And then I get x squared plus 4 squared multiplied by the derivative of the numerator, which is what? Negative 2x. And then minus negative x squared plus 4 times the derivative of the denominator is 2 times x squared plus 4 times 2x, right? So that's the derivative of the denominator there. Boy, and I'm just going to say that you are going to have to multiply out everything in the numerator, okay? And well, in fact, multiplying instead of multiplying out first, what you should be doing is factor out a x squared plus 4 first. So what you're going to end up with is x squared plus 4 times negative 2x. And then here I have negative 4x times negative x squared plus 4. Would you agree with that? If you do this factorization, then it's easier to multiply out and simplify inside the brackets now. And notice that I can cancel out a factor of x squared plus 4 as well and get a cube of x squared plus 4 in the denominator. Right? You guys agree with that simplification there? Everybody's okay? Now if you multiply out, what do you get? You get a negative 2x cubed, right? Oh, I could have factored out an x as well, right? Didn't I? Yeah, let's now factor out negative 2x, and then I'm going to get x squared plus 4 from the first from here, right? X squared plus 4, and then minus, since I am factoring out negative 2x, I'm going to get a positive 2x, positive 2, just positive 2, right? And then multiplied by negative x squared plus 4. I should have done that before, but let's do it now. And now if I simplify, what do I get? This will be x squared minus 2x squared, so that will be negative x squared. And I have a 4 plus 8, so that's what? 12. Divided by x squared plus 4 cubed. Okay. If you don't mind, I'm going to factor out a negative as well. So what that's going to do is give me a 2x times x squared minus 12 divided by x squared plus 4 cubed. And okay, so that's what I have. Okay, so all I did is found the first derivative and the second derivative. Finding the second derivative is, of course, a little bit more difficult and to simplify. And now I'm going to find the critical. So remember, the question was find the critical points and classify them. So how do I find the critical points? Well, I have to solve where the derivative is 0 first. And remember, what was the derivative? The derivative is right here, right? If this derivative is 0, it would mean what is 0? It would mean that the numerator is 0, right? If I say this quantity is 0, then the numerator would be 0. So that would mean that negative x squared plus 4 is 0, which would mean x squared is what? 4, which would mean x is plus or minus 2. So I have two critical points. Remember, I also have to solve where the derivative does not exist, right? Where the derivative does not exist. Well, can you tell me where the derivative doesn't exist? Well, it exists everywhere, right? Because x squared plus 4 in the denominator cannot be 0, right? This denominator can never be 0, so the derivative exists everywhere. So, no solution in this case. So I have only these two critical points here. And so then I have to classify them, right? So how I want to classify them by using the second derivative. That is, I want to know whether at -2 and 2 I have a local max and a local mean. Okay, is that clear? So so the critical points are these two. So in order to determine at -2 whether I have a local max or a local mean by using the second derivative, what do I have to compute? I have to compute the second derivative at -2, and if I compute the second derivative at -2, where is the second derivative? Here's I have second derivative, right? If you plug in, is it clear that the denominator is always positive? And if I plug in -2 for x, right, what do I get? I get 2 times -2 times -2 squared minus 12, right? That's what I get. And then I have -2 squared plus 4 here, whole cubed. And would you agree with me that this is positive? So I have a local max at x equals to -2. Oh, sorry, positive means local mean, right? I'm sorry. If the second derivative is positive, it means that the function is concave up. It means I have a local mean. And now I have to calculate what is f double prime of +2. And without doing any work, let me say it's negative. You can plug in 2 and see that you get negative. And so that tells you that you have a local max at x equals to 2. It's pretty easy to forget this, right? When the sometimes it's easy to make the mistake that if the second derivative is positive, then you have a local max. But think about in terms of the concavity. Second derivative